All right, people, some quick problems. Number one, place the following in order of increasing strength as oxidizing agents. In other words, we're going to put these things in order of the thing that will be least likely to be reduced to the most likely to be reduced. And to solve this problem, all we need to do is check out a reduction potential chart. I have Googled one here that has all of the different species that we are looking for. The first one there is the iron 2 ion. If I take a quick peek here, I'm just going to do a quick scroll for the iron 2 ion, which we see right here. It has a reduction potential of negative 0.41. So this one's going to be negative 0.41 volts. As we take a look at the chlorite ion there, and take a quick scan of our reduction potential list, the chlorite ion has a reduction potential of positive 0.59. So we've got positive 0.59 volts. Fluorine is going to be way down here. Positive 2.87 as its reduction potential. And then silver chloride, if we take a quick peek, it's going to have a reduction potential of positive 0.22. All right, so as we think about putting these on a list of increasing strength as oxidizing agents, in other words, we want to put it in order of the thing that's going to be least likely to be reduced, the thing that's most likely to be reduced. And again, you just want to look at the value of the reduction potential. In this case, the negative 0.41 volts, which is our iron 2 ion, is going to be the least likely to act as an oxidizing agent. Then we've got the 0.22. We've crossed into the positive voltage area, but that's going to correspond to our silver chloride. From there, we've got the positive 0.59 volts. That corresponds to our chlorite ion. And then lastly, the strongest oxidation agent, or the thing that's most likely to be reduced, is our fluorine molecule there. So again, to answer this question, you would either have to be provided with the standard reduction potentials, or you would have to go to a standard reduction potential chart and look it up for yourself. So this problem is really just asking you, do you understand what the reduction potential chart is telling you? So bear in mind, it can get confusing. I had to reference the internet to figure out the reduction potentials for some of those species that we were working with in that problem. I really like this reduction potential chart from Flynn. It really helps me sort of keep straight in my mind what's going on, because we're throwing an oxidizing agent and things being reduced and all this other stuff. And so this one's really nice, I think, to help you sort of get your mind wrapped around what this information is telling you. Again, the higher that reduction potential, the more likely the thing is to be reduced. And again, when something is reduced, it acts as an oxidizing agent. So a lot of terminology here that can get really confusing, but if you take a couple minutes, just sort of get it straight in your mind, you'll be set for the rest of the year. Okay, problem number 2 here is going to give us a look at some of the big things that we are going to have to be able to do with galvanic cells. I'm going to just give myself a little reminder up here at the top. Red cat, anox, and fat cat. Just some mnemonics I like to keep in my mind when I'm doing these problems with galvanic cells, to remind me that reduction occurs at the cathode, that the anode is where oxidation takes place, and that the flow of electrons is from the anode to the cathode. So Just some things to keep in mind. I would encourage you to commit these mnemonics to memory. It will really help you when you're working with these galvanic cells. Okay, so first things first, we take a quick look at the two reduction potentials that we are given here. The very first thing we want to do is just compare the two values. We've got a positive 1.70 volts for our standard cell voltage of this reduction half reaction, and we've got a negative 0.14 volts as the standard cell voltage for this reduction reaction. So as we're trying to figure out what's going to happen in this galvanic cell, the thing that's going to have the largest positive reduction potential is the thing that's going to be reduced. So I'm just going to put a little note here, reduction. It's got a higher standard cell voltage. So reduction is going to be here, which means that oxidation is going to happen in the other half cell. Now, keep in mind the reaction is written as reduction, so when we write out our galvanic cell here, we're going to have to flip that reaction. So, we've got Ce4+, gaining an electron to form Ce3+. And our reduction potential for that half reaction is going to be positive 1.70 volts. We're going to flip the second reaction. So we're going to get solid tin losing a couple of electrons here to form the tin-2 ion. And our standard cell voltage here for this oxidation half reaction is going to be positive 0.14 volts. So notice there that I had to reverse the reaction because we're going to have the oxidation half reaction occur there. And all you need to do is make sure you change the sign of your reduction potential to indicate the oxidation potential for that half reaction. Now, before we go any further, we want to make sure that we are gaining as many electrons as we are losing. And as it's written right now, our oxidation half reaction is showing the loss of two electrons, but our reduction half reaction is showing the gain of only one. And so the first thing we want to do is just use a whole integer multiplier here so that our number of electrons will cancel out. It's important to note that when you're doing this, you're not going to multiply your reduction potential. When you do that, you're just going to add those coefficients. The reduction potential will stay the same. Then we're going to combine our two half reactions to create our one complete redox reaction. We're just going to get the things on our reactant side. And the things on our product side. So the standard cell voltage for this redox reaction is going to be positive 1.84 volts. Let's do a quick diagram and then draw a quick picture to help us answer some of the last things that this question is asking us to complete. If we start with the cell diagram, again, you want to put your anode on the left-hand side. And remember, oxidation occurs at the anode. The oxidation half reaction is this one here. So we're going to start with the tin electrode, and it's going to be in a solution of tin-2 ions. Will be connected by a salt bridge, 2 lines, to our reduction half cell. And it's kind of interesting to note here in this example that we don't have a solid electrode here. We've got these ions, and the reduction is going from a positive 4 charged ion to a positive 3 charged ion, but we don't have a solid electrode here. So in a case like this, you're just going to include the ions and then to complete the galvanic cell, you will have to use an inert electrode in order for those electrons to flow through. Platinum is always a good one to use. You can also use carbon electrodes as sort of an inert electrode, but go big when you can. When you're not buying it, right? Go platinum. So this represents our cell diagram. If we then draw out a picture of our voltaic cell, we're going to have one half cell here, second half cell here, connected by a salt bridge. Boop. Boop. I'm going to then put my tin electrode in over here. So this is tin. And then my platinum inert electrode in over here. We're going to connect this with a wire. Boom, there's my wire. And then we've got our solutions in here. Our solutions are going to be, let's see, in this one we're going to have the tin 2 ion. And over here, again, because our reduction half cell is going to have just ions, we'll include both of those ions in our solution. For your salt bridge there, you can put any salt, but I commonly use potassium nitrate. It's always a good one to go to in terms of the salt that will be in your salt bridge to replace the charge as the reaction takes place, and to ensure that your reaction doesn't stop. The last thing that we need to do is indicate the direction of the electron flow. The electron flow is going to occur from the anode to the cathode. So again, remember fat cat. Our anode here is the tin anode, and so our electrons are going to flow in this direction. And again, as those electrons flow down that inert electrode there, the 4+ ion is going to pick them up and be reduced to the 3+ ion.